Hello, good evening. Welcome to the course of Nanotechnology Science and Applications. In this course, till now we have studied about the introduction to nanomaterials, what is nanotechnology, and the science behind the of properties observed, and finally we studied about the applications. Till now, we have conducted around 6 weeks of this course, where we learned in a great detail about various aspects of nanotechnology, its properties, and how these properties can be varied, how it affects the mechanical properties, how it affects various other electrical properties, and various other properties. The course coordinator for this course is Professor Pratap Haridos from IIT Madras, and I will be the course teaching assistant for this course. This is the week sixth of the course, and in week six we'll be learning about the optical properties of nanostructured materials and how the optical properties are affected due to the involvement of nanoparticles. We'll be studying about that. So yeah, let's begin the course. A brief recap of what we learned in the previous classes. First, in the initial weeks, we were introduced to nanomaterials, like what are nanomaterials, how is nanomaterial defined. We define nanomaterials as the materials in which either at least one of the dimensions is less than 100 nanometers. Then we categorize nanomaterials and classify nanomaterials on the basis of various properties, on the basis of various classifications to various types, on the basis of dimension, on the basis of natural or man-made nanoparticles. We divided into various, classified them into various types. Then we discussed about the synthesis of nanoparticles. The main aim of the synthesis is getting an identical size and composition, identical shape, morphology, and monodispersed nanoparticles. So, on the basis of these aims, we discussed two types of approaches to produce nanoparticles. One is top-down and bottom-up approach. Then we discussed about how the nanoparticles influences the properties of the material. Like we discussed about how thermodynamics and kinetics affect the properties. Uh, we studied that thermodynamics and kinetics affect the microstructure of the material, which in turn affect the properties of the material. And these nanoparticles change the thermodynamics and kinetics of the processes. So that means if something changes the thermodynamics and kinetics of the processes, it in turn changes the microstructure, and finally it changes the properties of the material. Then we studied about various how improvement of strength occurs. We studied about Hall pitch relation. We studied about inverse Hall pitch relation. We studied about strengthening mechanisms, like how decreasing the size of materials to nano range helps in strengthening. How the grain size helps in strengthening. How the parameters helps in strengthening. We studied all of this. Then we discussed about wear rate, like how nanoparticles helps in the nanostructured materials helps in improvement of wear rate or decrement of wear rate, helps in the increase of wear rate or decrease of wear rate or improvement in the wear resistance of the material. We discussed about that. We discussed about various examples as to how weight loss and wear can be related to each other. And then finally, we discussed about ferroelectric in the previous classes, ferroelectric materials, BATiO3 materials, how their structures affect the how their structures are arranged, and how this arrangement of atoms affect the properties or affect the electrical properties of the material. We studied about this, and today we'll be studying about another property which is affected by the nanoparticles or the nanomaterials is the optical properties. What is optical properties? As you can understand, optics means light. So these properties depend. These properties are which are sensitive to light, or how light reacts to this light. Visible light reacts to these materials, or how these materials react to visible lights. Sorry, how these materials react to visible light, and um, what changes can we do in the nanomaterial range which can affect the optical properties of the material. Let's forget about nanoparticles for now. Let's think about one thing for now. What we learned in our previous undergrad or high school courses, we studied about conduction band and valence band, right? What are these? The valence band had electrons in them, and the conduction band does not have electrons in them. So what we studied, if the electrons from the valence band is transferred to the conduction band, then all the properties, the electrical properties, and any other properties will be seen in the material. In the previous classes, we learned that to take this electron from a valence band to a conduction band, we need to apply some energy. Otherwise, how will the electron move? The electron is sitting in its very stable position in the valence band. To disturb its position or to send it to the conduction band, we have to apply some energy. And this energy is the difference between the energy of the conduction band and the energy of the valence band. And this is known as the band gap of the material. So if the energy we are supplying to the material overcomes the band gap, the electrons which is taking up the energy overcomes the band gap of the band gap between the conduction band and the valence band, then the electrons in the valence band will be able to jump to the conduction band, right? Then we can get the various properties. So this is the explanation which we learned in our high school level and undergrad level about the valence band and the conduction band. And we learned that in metallic structures, the valence band and the conduction band, they overlap each other. There is no distinction, there is no band gap between them. So most of the electrons in the valence band are also in the conduction band. So that means no high energy is required for the electrons in the valence band to jump to the conduction band because they are overlapping each other. They can they get transferred easily from the valence band to the conduction band. Then comes, let's think of a situation where the conduction band and the valence band have a small band gap between them, very small band gap between them. This is the case of semiconductors. So what will happen in this? In this, we need to apply some energy. So we need to provide some energy for the electrons in the valence band to jump into the conduction band. The energy may be small, but we need to apply some energy for that jump. Then finally comes the insulators. What happens in insulators? The gap between the conduction band and the valence band is too wide. So we need to apply more energy so that the electrons from the valence band will jump into the conduction band. It requires more energy because the band gap is high. So to travel from this energy level to this energy level, we need to supply more energy to that material. That is known as insulator. So think of a situation like when you are let us suppose the energy we are having is visible light, and visible light is the energy source, as I said earlier, and the visible light ranges from you remember Vibgyor, right? Violet to red. So from violet to red, from blue to red, which we say the difference in the energy or the range of energy is from 1.8 to 3 electron volts. This is the range of energy from violet to red. So when we're supplying visible light energy to a material, what will happen? This much range of energy is being applied to the material. So if the band gap is smaller than this much energy, what will happen? Some of the electrons in the band, some of the electrons will be able to jump to the from the conduction band to the higher energy level, that is from the valence band to the conduction band. So in metals, what will happen? Be it be very less amount like 1.8 electron volts, or be it be 3 electron volts towards the higher side, anything we apply, it will always jump from the valence band to the conduction band because they are overlapping each other. That means any energy we are applying to the material is getting absorbed in the material because because they are overlapping to each other. So any energy from 1.8 to 3 electron volts, anything we are applying gets absorbed, because some electrons will be there at which will be requiring 1.8 electron volt, or then there will be some electrons which will be requiring 3 electron volt to jump from the valence to the conduction band. So the whole visible light which we were applying to the metallic samples get absorbed, because the whole energy is getting absorbed. So if the light we are applying to the metallic sample is getting absorbed, so the metals will appear opaque. There will be no light in the material. This is what is happening in case of metals. Then come to the semiconductors. In semiconductors, you see a small band gap. And let us suppose that in generally which is seen in semiconductors, that this band gap is approximately the maximum energy of this band gap is 2 electron volts maximum. So anything less than 2 electron volt of energy, what will happen to that? So I'm telling you the maximum band gap will be 2 electron volts. So if we apply an energy which is exactly at 2 electron volts, the the material, the electrons in the valence band of the semiconductor will be able to jump to the conduction band. This is happening, right? So 1.8 to 2 electron volt, anything, any energy we are applying, the electron in the valence band will be able to jump to the conduction band. This is applying. So that means what is happening? So there is some range of energy which is being absorbed by the semiconductor, and there will be some range of energy which will be passing through the semiconductor. Like there is some range which can be absorbed because the electrons has to jump from valence band to the conduction band, and the rest of the energy which is not absorbed will be released. And the released energy has a frequency, and that frequency will be falling in some of the from Vibgyor, that energy will be falling in some of the colors, will be falling in the spectrum, eh, with some of the colors, and these colors are being reflected as the colors of the semiconductor, because these energies are not absorbed by the semiconductor. These energies are given out, transmitted. So these energy is the equivalent color, the equivalent spectrum of this energy which is transmitted is shown as the color of the semiconductor. Then we consider the extreme case, like the band gap is too high, more than 3 electron volts. So if the band gap is more than 3 electron volts, that means any visible light we supply to that material, it will not be able to excite the electron in the valence bond to the conduction band, because the in a band gap is more than 3 electron volts. So maximum energy from 1.8 to 3 electron, whatever we are applying, everything passes out through the sample or is transmitted through the sample, because none of them are being absorbed to excite the electrons in the valence band to the conduction band. So all the electrons are being, sorry, all the visible light, all the, uh, excuse me, all the energy or all the frequency which is applied as a source of energy are being reflected or are being transmitted. So the material appears transparent. That's why all the insulators they appear transparent, because all the material, because energy, the band gap between the conduction band and the valence band is so high that the energy or the visible light which is being applied to the material does not excite the electron from the valence band to the conduction band. That is what we are observing. So we got an idea about what optical properties are. Now let's. There's a question. Sorry. Uh, you said no in something. Can you elaborate? What was the question? Oh, sorry. Sorry, I missed your answer to that. Was it like? Um, did you understand what I was trying to say, or because I forgot what I asked actually? Did you understand what I was trying to? Okay, fine. Thanks. Thanks a lot. Yeah. Yeah. So we understood what is happening in case of optical properties of the material. Now let's, as we are in the study of nanoparticles, let's see how nanoparticles will be affecting this. Of course, nanoparticles will be affecting the band gap of the material, but how is it affecting? Let's see. What is happening in nanoparticles? In nanoparticles or in nanostructure materials, we are introducing grain boundaries. For example, recall about the nanostructured materials we talked about during the Hall patch relationship, during all other relationships, during the grain, sorry, rolling and all. What we're doing, we are refining the grain size during all extrusion, equiangular extrusion and all. In that, we are refining the grain size. That is, we are introducing the grain boundaries, right? So when we are introducing gain boundaries and we are introducing porosity, introducing grain boundaries is because now we want nanostructured materials. So we want nanoparticles. We are introducing gain boundaries or nanostructure gain boundaries. Then another point is we are introducing porosity. If we introduce porosity in the material, and this porosity will be in the nano range, very minute porosity. We are introducing a very size of the porosity is very less. If we are introducing these two into materials, we observed that the material which was transparent, so let us suppose an insulator, which is a material which is transparent, goes from being an insulator to being a metal, or not from an insulator to a metal, the band gap decreases. That means the color of the material from insulator which is transparent to and which is transparent in insulator will go into an opaque, as in the case of metal examples. If we introduce nanoparticles in the material, this is what is happening if you introduce nanoparticles. So from transparent, it moves into opaque. And transparent was in higher band gap, what we have observed, and opaque material were in very low band gap. So by introducing porosity or grain boundaries, and these two will be present in the nano range, what we are doing, we are making the optical properties or transferring the color of the material from transparent to opaque. This is what we are doing. And the reason for this is the interfaces. We are introducing interfaces in the material, and these interfaces will help in the transformation. from transparent to opaque. Yeah. Then there was a discussion about various band gaps. Actually, the very detailed discussion was done by Professor Pratap Haritos. I will not be going into so much details about this discussion, but some of the ideas of what he discussed, I will be explaining you, which will be helping you to answer the questions in the assignment. If there are still doubts in the assignment, you can always ask in the live chat. Yeah. Then another concept he introduced about this band gap is direct band gap and indirect band gap. And he said that let's see what is that. Then we will be discussing what he said. The direct band gap is a thing. Here you can see this is a conduction band. This is a conduction band, and this is a valence band. This is a valence band, conduction band, valence band, as I show you in the previous slide. What happens in a direct band semiconductor? The top of the valence band and the bottom of the conduction band occur at the same momentum. The momentum, as you can see here, the momentum they are means below the bottom of the conduction band there is a valence band present. This is the top of the valence band present. The band gap is remaining same everywhere in case of a direct and indirect direct and indirect band gap. But the difference here is that the bottom of the conduction band and the top of the valence band are in coherence to each other, or are in same value of momentum. So the transfer of electrons will be easier in this. Like from the valence band, it will directly jump into the conduction band because it's in the same momentum. It will directly jump into the conduction band. So that means there is an efficient way of absorbing the incoming electrons because they are in the same momentum. So there is an efficient way of absorbing the electrons here. So that's what Professor Pratap was trying to explain. As he said that in direct band gap, there will be an efficient absorption of incoming radiations or electrons. Because this is the thing. But what happens in an indirect band gap? The top of the valence band and the bottom of the conduction band are not in coherence or not in momentum with each other, or have a different value of momentum. As you can see here, it's not exactly above that. Though the band gap remains same, it's not exactly above on the top of the valence band. So for the electrons to jump from valence band to the conduction band, it has to travel through this distance. This much will be the energy required for the travel, which is quite high, as you can see here, which is quite high. So therefore, Professor Pratap explained that in indirect band gap, there is an inefficient in absorption of radiations, incoming radiations, because they are not in momentum with each other. Then they have a different value of momentum. So that means the jump of the electrons from the valence band to the conduction band will be difficult here, or there will be an insufficient absorption of electrons because of this. So this is the difference between direct band and indirect band as he explained in his lecture. Then I think he explained about various energy diagrams and various atomic level diagrams, which I will be not going through this because more details will always be, we can always refer back to his presentations. But still, if you have doubt, you can ask me. Then he introduced one another concept, how to manufacture nanoparticles, or how this nanoparticles affect the properties of the material, is by introducing naphion. What is naphion? Let's have a look into that. There is a term of template assisted synthesis, and in template assisted synthesis, what is happening? In template assisted synthesis, that means we are synthesizing nanoparticles with the help of a template. I will explain you where a Nafion came from, but let me introduce you to first one concept, that is template assisted synthesis. Because we talked a lot about the synthesis of the material, like various things about the synthesis. We talked about top-down approach, bottom-up approach, various types of synthesis mechanism. This is also another synthesis mechanism, template assisted synthesis. As you can see here, template assisted. That means the synthesis of the nanoparticles is assisted or is helped with the help of template. And the template here is Nafion, as he discussed in the class. So this is the structure of the Nafion. Just a second. This is the structure of the Nafion polymer. This is the structure. It's a polymer, so it has CF bonds, CC bonds, and CO bonds. As you can see here, it's a polymer. But the main thing to observe here in a Nafion polymer is that uh, it is a ionic compound or ionic polymer. Here you can see here SO3 minus here, and H plus ions, which are free bonds. Here everything is bonded. You can see everything else is bonded here. But this SO3 and H plus ions are different. So this attachment here, that is this SO3 minus and H plus here, will help in the ionic showing the ionic property of the molecule, ionic property of the polymer. So one thing we can do here, or one thing people do here, what they do, the SO3 minus and the H plus is there, people replace this H plus by some other nanoparticles. This H plus ion can be replaced, and people replace it by some other nanoparticles. Then they will follow the procedure. You are replacing. See, the nanoparticles, as we discussed, have a tendency to agglomerate among each other. So people have tried to prevent this agglomeration. How can we prevent this agglomeration? By using a template assisted synthesis. But the disadvantage of this method is that, as you can already tell, because it requires a lot of things, like we have to replace the H plus by some other nanoparticle. Then similarly there will be a multiple polymers of this Nafion, and this everything will be replaced one by one. That means the large scale production is very less. It's never possible in large scale production. Only small scale production is possible in this. So what is happening in this Nafion polymer? It has some pores in the material. This let me show you the diagram. The Nafion polymer has some pores in the material, and this SO3 minus and H plus is present along the pores. This is the structure of the Nafion. So what is happening when we are replacing this H plus ions by some nanoparticle here, in this only it will be replaced. The H plus ions will be replaced, right? So that means this spore does not have any relation with this spore. They are not touching each other, or they are not in connection with each other. So that means the nanoparticle in this spore will be different from nanoparticle in this spore, and there is no chance of agglomeration of these nanoparticles. This is what the advantage we are getting by assisted synthesis. And the size of the nanoparticle remains the same because the pores are not interacting. How will the size of nanoparticles grow? When they agglomerate with each other. So the size of the nanoparticles is controlled within the pores. Stable nanoparticles can be synthesized because they are not interacting with each other. There is no relation between two pores, so the stability is maintained. But the disadvantage is that it can handle only very small number of particles. It cannot handle a huge amount of nanoparticles. So industrial scalability is very less in this process, template assisted synthesis. And what you are doing when we replace the H plus with the with any other nanoparticle, then we are evaporating it out. We have to remove this polymer. We have to remove this polymer structure because we don't need this. We just need the nanoparticle. So we are evaporating out. We have a various techniques as explained by Professor Pratap. We are using films. We are using H2S medium to remove out the template. Then we have now the nanoparticles. The nanoparticles which was used by replacing H plus. So now we got the nanoparticles which are not agglomerating with each other. So the advantage of assisted synthesis is that we are enabled to synthesize the particles with controlled sizes. As I explained, controlled size is controlled. Then the stable particles are synthesized because they are not interacting with each other, they are not agglomerating. The stable particles are synthesized. Then it can handle only a small number of particles. As I said, told you earlier, the industrial scalability or more like the large scale production is less in case of this templated assisted synthesis. This is what we discussed, Professor Pratap discussed about replacing H plus with PBS, how they are physically separated, and how it leads to the production of nanoparticles PBS. He discussed about that. I will not be going into detail about this. Then comes various characterization techniques, which can show like how the properties are changing in case of nanoparticles, or if nanomaterials are introduced, or if nanostructured materials are present, how the properties are changing. So some of the characterization techniques we will be learning. First is the X-ray diffraction. As a material scientist, always what you do, the basic starting point to identify, you're given a material. The basic starting point to identify a material is by doing the X-ray diffraction. You have seen a lot of X-ray diffraction peaks, but these peaks give a large amount of information. Not only that, it shows the peaks. Okay, this is the comparison. We'll be comparing it to the acidity patterns, and we'll be telling that okay, this is this, this is that. Not only that, it says a lot of things about strain, about phase, about how the FWHM is varying, that is full with half maxima is varying, and why there is a fake peak shift, why there is a peak, why there is a peak shift, why there is a peak broadening. Everything will be explained with the help of X-ray diffraction technique. So this is a basic technique which can give you an idea about lot of things about the material, even if you don't know the microstructure of the material. You're given a material, you will do an XRD, you will know a lot of things about the material. Like what are the phases present, what are the strains present in the material, or why there is a peak broadening in the material, or how much broadening is there in the material, where there is a peak shift in the where there is a shift in the peak of the peak observed in the from the XRD data. Everything will give you a reason, or everything will say you something about the material. This is why we are doing X-ray diffraction. And this X-ray diffraction depends on various law. And the first law it depends on is Bragg's law. Bragg's law, which came from the interference, constructive interference of the waves of the X-rays which we are applying. From that, we got to know that there is a equation lambda equals to n lambda equals to 2d sine theta. This is Bragg's law. Where the theta, what is theta? The theta is this angle. 2 theta value is this angle which you are seeing. And lambda is the wavelength of the X-ray you are using. You are irradiating some X-rays on the sample, and then you are getting this peak, getting this value. So lambda is the wavelength of the irradiating X-rays. Then D here is the interplanar spacing. interplanar spacing between the planes of the inside in the crystal structure. So you can see here so many things. You're getting the interplanar spacing, and if you have a standard sample, you have an interplanar spacing of that sample. So comparing this interplanar spacing with the value you observed, we can get the strain in the sample. There are a lot of informations you can get from this XRD, as I told you. So this is what XRD gives us, and this is the Bragg's law from which we can extend this Bragg's law to a lot of things. Scalar's formula, and extend this Bragg's law to a lot of things, and we are getting a lot of information from this Bragg's law equation. Another point to note here is that as let's come back to, because we are talking about nanoparticles, let's come back to nanoparticles. We know now what XRD is capable of, what X-ray diffraction values give. Now let's study how nanoparticles affect this X-ray diffraction. uh, let's talk about this figure first. As you can see here in this figure, this is a XRD pattern of a stainless steel 304L stainless steel, austenitic stainless steel. So as I told you earlier, this is an austenitic stainless steel. So the austenitic stainless steel has a FCC crystal structure or FCC structure or FCC phase. Austenite is an FCC phase. So you will be getting peaks only in the FCC regions. So this is the first peak you are observing. This is the second peak we are observing. This is the third peak you are observing. So all the FCC materials have these three peaks. You can observe these three peaks in all the FCC materials. And so this you can confirm that this is an FC, this can confirm the phase of the material. As you can see, these three peaks. This can confirm that what is the phase in the material. Then you can finally identify with the help of ICDD comparing with ICDD patterns. Then you can identify that this is 304L stainless steel because the positions of the peaks will be changing, and this will be compared with the ICDD patterns which we have earlier. Another point to note here is that you can see these peaks are quite sharp, like they are almost a straight line. You can see they're almost there is a small peak broadening observed, but they're almost straight lines. They're almost straight lines, as you can see here. They're almost straight lines. In case of a bulk sample, this is a stainless steel bulk sample. However, when you come into the nanoparticles, what is happening? Let's see. This is GNS. This is GNS is graphene. Graphene, and along with that, there are some bonds with the graphene. That's why it's known as GNS. But this is a graphene XRD of a graphene. And graphene, as you know, is a nanoparticle, nanomaterial, nanomaterial. So what is the difference you're observing? You see, there is a peak broadening. Clearly, there is a peak broadening. You can see. See, there is a completely a straight line, and here you can see almost 10 degrees of broadening you are observing here. Here you can see there is almost nil. The broadening is almost nil. This is 10 degrees of broadening. As you can see in this peak also, there is a huge broadening of this peak. Another point to note here is the intensity. See, the here the intensity is too high, but here the intensity is too less, and the broadening is too more. So this is what is observed by the nanoparticles or nanomaterials. What is the reason for this? The reason for this comes from Bragg's law. This will define why what is happening to this nanoparticles. So as I told you earlier, this Bragg's law came from the constructive interference patterns, right? You're solving the equation for constructive interference. Then here n lambda as you saw is constructive interference. Like you are observing this peak or you are observing this intensity or the intensity of the material is observed when there is a constructive interference. And why this you will say that there should be a peak here also, why it is not visible? Because here also there is a plane, but why it is not visible? Because This peak is out of phase. This is not constructively interfering, it's destructive interference. So that's why this is missing. This peak is missing in the metallic samples. However, where the constructive interference takes place, those peaks are visible in case of metallic samples. Understood. But in case of nanoparticles, what is happening? This uh, we are talking about destructive interference. What is destructive interference? There are some planes of atoms, and for example, there are 50 planes of atoms which are constructively interfering. Like they want to constructively interfere to give the peaks. But there are 50 other planes which are destructively interfering. Like the the constructive interference occurs by 50 planes, and there will be other 50 planes which you will be counter opposing this constructive interference. So the intensity is diminished or lost because the positive constructive interference and destructive interference, they cancel each other out. In case of nanoparticles, what is observed? The amount of material which is constructively interfering is present. But as we are shifting to nanoparticles, we are decreasing the amount of planes because we are shifting to nanoparticles, and this is bulk material. There are a lot of planes, but we are shifting to nanoparticles, so decreasing the amount of planes. So there will be not sufficient enough planes to destructively interfere these constructive interferences. That means there will be some decrease in the intensity, but the intensity will not be lost. Therefore, you're observing, therefore, you're observing a peak protein because the intensity is not lost here. There will be some intensity present in this because everything the material which are constructively interfered are not completely destructively interfered by the other half, because the other half is not present, totally not present. Some amount will be decreased, the intensity will be decreased, but it will still be present as compared to the bulk material samples. That's why you're observing a peak broadening as well as decrease in the FWHM or the full width height maximum value. More into this details, you can always refer to Professor Haridos's lectures. If you still have doubts, you can ask me, or we can discuss it in the discussion forum. So this was about the X-ray diffraction. Then another point we studied about is optical absorption spectra. Optical absorption spectra. This is also a technique which will show you how the nanoparticles are affecting the absorption spectra. As I showed you earlier in this in the presentation, that there will be a we like there's a band gap between the conduction band and the valence band, and we are continuously applying some light or some energy to the material. So wherever the energy will be absorbed, there will be there will be a jump of the electron from the valence band to the conduction band. So when the electron is absorbed, or when the electron jumps, it absorbs the energy which is provided to it. So that means when we plotted this against wavelength, we saw that the absorption intensity, this is the absorption intensity against wavelength. We saw that when we go from a higher wavelength to a lower wavelength, at a particular wavelength, there will be a huge increase in the intensity. That is, all the energy we are providing to the material is being absorbed by the material. That means that at that wavelength, the energy we are providing is equivalent to the bond energy, or is equivalent to the band gap of the material, because at that point all the energy is absorbed. That means that is the band gap, like that much energy is absorbed. Okay, all the electrons are jumping into the conduction band at that point of energy, at that point of wavelength. So So at this point, we observe that there is a this is known as the band gap. Sorry, band gap. This is the energy of the band gap, or this is the as this is a wavelength plot. This is the wavelength of the band gap. You know how to relate wavelength to energy, right? E equals to h nu equals to Planck's constant h c by lambda equals to h nu hc by lambda. Planck's constant and hc by lambda is lambda here is the wavelength. C is the speed of the light. Nu is the frequency. So for every energy there is a particular lambda, right? Because h you cannot change. Planck's it's a constant. C you cannot change because it's speed of light. You cannot change. You can only change lambda. So for every energy there is a lambda. So for every lambda, you see, for every lambda there will be a particular energy. So at this point, there will be a particular lambda, and at this lambda, there will be a particular energy. And as I told you earlier, this will be the energy of the band gap, beyond which the material absorbs everything. But now let's come to the nanoparticle. What is happening in case of nanoparticles? In case of nanoparticles, what is happening? We see what I told you earlier in the earlier slides. What I told you earlier, like uh, just check about these relations. When the lambda increases, the energy decreases, and when the lambda decreases, the energy increases. Right? That means here it is higher lambda. Higher lambda means the energy is low here. Energy will be lower here, and here the energy will be, what will be the energy? Higher, because the lambda is low. They are inverse proportional. The lambda is low. So the energy is higher here, the energy is lower here. What we are observing in nanoparticles is that this graph shifts towards left. If we increase the nanoparticle size, the graph shifts towards left. It will become like this. That means the band gap, what is happening to the band gap? The energy is the wavelength is towards smaller side or shifting towards the smaller side. So what is happening to the energy? The energy is moving towards the lower higher side, because the lambda is towards the lower side, so the energy is moving towards the higher side. So higher side movement of energy, that means the band gap is moving towards a higher energy level, or higher energy. Higher energy corresponds to which color spectra of from the Vibgyor? It is called, it is the blue one. The blue one has the higher energy, blue light. That means when we decrease the nano size of the particle, or when we are reaching the nanoparticle range, when you're reaching the nano size range, there will be a shift towards the blue region. This is known as blue shift. There is a question in the assignment of blue shift. What is happening? This is known as blue shift. So when we decrease the size of the particle, or decrease the size of the particle towards nano range, there will be a shift in the uh, band gap towards the blue region, which is known as blue shift. Then we studied about TGA, another process called TGA, and the TGA I will be not be covering in this lecture today, because it was the TGA was explained by Professor Pratap in a very mm, uh, um, detailed way, like what is happening, how there is a question on TGA also, like what is the difference in the if there is a change in the temperature, what is happening, why there is a range of temperature, why there is a range of temperature for the removal of water molecule, then after some range of temperature what is happening. There's a question related to TGA in the assignment too, like what is happening in case when there is when the material is subjected to 400 degree or something. I couldn't remember the question, but it was somewhat similar to that. You can answer that, like what is happening in this range, after that what is happening. So we can say what are the points which is happening in case of when the temperature is from that to that. So that can be answered very easily in case of TGA. So I will not be covering that. These are some I'm just covering some of the extra things or some of the points which can help you to answer some of the tricky questions in the assignment. So then we studied about the conductivity of the membrane, like how the ionic conductivity is measured with the help of electrochemical impedance spectroscopy. There is a graph which we got from there. We found how the ionic conductivity was obtained. Then we drew the circuit to find out the resistance which is offered by the solution and all. Then one more important thing to discuss here is that as we are discussing the what characterization techniques like XRD, optical absorption spectra, we're discussing this. Let me just introduce you to another another technique of characterization known as the transmission electron microscopy. So what is a transmission electron microscopy? Transmission electron microscopy is a kind of characterization technique where we are going into the nano range of the, or we are magnifying the material to very nanoparticle range. So nano range, so that we can observe what is happening in the nanoscale. Because nowadays the technology has improved so much that we can engineer the particles in the nano range. So if we engineer the particles in the nano range, we should be able to see the particles in the nano range. This is what is the TEM helping us to do. TEM helps us to see the particle size, as you can see in this image. It helps us to see the particle size. See, the particle size can be identified. There is a scale bar, and you can identify the what is the size of the particle. So approximate size of the particle is identified from the TEM image. This is done for metallic samples too, not only for other samples. For metals also, we can view what is happening in the nanoscale range with the help of a TEM. But the problem with this technique is that, as I told you earlier, this is a bulk sample. This is a bulk sample, and we are going into the nano range. We are observing in a TEM image. We are going into the nano range. That means, so we are observing only this portion of the material. Because let's suppose this is size of 10 nanometers. We are observing this portion of the material, just this portion. We cannot observe the whole material. So what we are observing in this, we are extrapolating the same result to the whole material. We will be saying that, okay, this is observed for this portion of the material. So the same will be observed for all other portions, and we'll be extrapolating the results. But in case of XRD technique, which I discussed here, what is happening? This is another calculation technique. What is happening? We have a sample and we are just applying X-rays to the sample, and we are obtaining some other rays, and we are detecting this through a detector. So that means the X-rays will be interacting with the material in a wide volume rather than the TEM what we saw in a very small area. So some of the researchers accept X-ray diffraction as a better method rather than TEM or any other method to describe the status or describe the state of the sample. But some people use TEM method to describe the state of the sample. It depends on how are the applications, of what applications are you looking into. That will determine your method of characterization in case of nanoparticles. So this was all about today, like what we discussed, like what is TEM, how they are helpful. Then we discussed about XRD, different techniques such as XRD, optical absorption spectra. We discussed about synthesis assisted, template assisted synthesis mechanisms. How are they helpful? Then we discussed about the optical properties, like what is the difference between conduction band, valence band, how the electrons are transferred from valence band to the conduction band, what is the band gap. We discussed about that. Yeah, I think I have covered all the questions in the assignment, but still, if you have some questions, you can drop it in the chat box or you can ask me now. Yeah, I'm all up for questions. If there are no questions, then we can conclude the session. Okay, there are no questions. Okay, then. Thank you so much. Thank you for attending. Have a good evening. Thank you.